Hello, this is the first lecture for Chapter 4, Climate Change Notes Part 1. Chapter 4, with a focus on climate change, will have the objectives of studying one of the more popular elements on the periodic table, and that element is carbon. So we're going to learn about the different sources and locations of carbon on the Earth. And these locations where carbon exists on the Earth are called reservoirs. And we're going to study how carbon moves between reservoirs on the Earth and how the amount of carbon in these reservoirs are measured by scientists. And then we're going to talk about greenhouse gases, what they are, and what their positive and negative effects are for the Earth. And we're going to look at some global consequences of climate change and how our current climate trends differ from those climate trends of the past. And finally, how our daily actions affect the global environment. So carbon, again, is a very important element on the periodic table because carbon can be found in all living things. And there is a specific division of chemistry called organic chemistry that focuses specifically on studying and producing and synthesizing carbon-based compounds. And so carbon can exist in many forms. It can exist in many forms by itself, and it can exist in many forms as a part of compounds that contains other types of atoms as well. So carbon can exist in many forms by itself. And so when a substance only has carbon atoms, carbon is then described as being existing in its elemental form. So there are three main elemental forms of carbon, and those are graphite, diamond, and Buckminster fullerene. Buckminster fullerene is also called C60 because it is composed of 60 carbon atoms bonded together. Graphite and diamond also only consist of carbon atoms bonded together. But what makes graphite, diamond, and C60 different from each other is the way in which those carbon atoms are arranged and bonded to each other. Carbon also exists in many very important, notable compound types. Some of those different types of compounds in which you'll find carbon atoms are sugars, like glucose. It has the formula C6H12O6. So there are 6 carbon atoms in glucose. And then your everyday table sugar, which is called sucrose, it has the formula C12H22O11, having 12 carbon atoms. So in addition to sugars, something that we intake into our bodies on a daily basis, another popular compound type that consists of carbon atoms are alcohols. Things like ethanol, which has the formula C2H5OH, having 2 carbon atoms, and other alcohols like isopropyl alcohol, which is your common rubbing alcohol that you buy in the drugstores. It has 3 carbons, its formula being C3H7OH. And then in addition to sugars and alcohols that contain carbon, another very popular class of compounds that contain carbon are your hydrocarbon compounds. Hydrocarbon compounds contain only carbon and hydrogen atoms. And so hydrocarbon compounds can be found in substances like crude oil. And crude oil contains a mixture of different hydrocarbons like methane, CH4, others like propane, which is C3H8. Propane, you may have a gas grill that uses propane. Also butane, C4H10. Butane is the type of fuel that you find in little strikers that you use to light your fireplace, or same type of fuel that you'll find in cigarette lighters, for example. Then there are various other types of organic compounds. Some you may have never heard of, things like esters and ethers and aldehydes and ketones. One of the more popular ketones is the ketone acetone, which is found in nail polish remover. It has the formula C3H6O. And then, of course, you have carbon in carbon dioxide. And so where is carbon located on the Earth? It's located in reservoirs, and there are four main reservoirs for carbon on the Earth. The first reservoir for carbon is the atmosphere. In the atmosphere, you have carbon in the form of carbon dioxide, CO2. CO2 in the atmosphere has a concentration of about 400 parts per million. Then there's also methane, CH4, which has a much lower concentration in the atmosphere than carbon dioxide, only 1.8 parts per million. And then there's also carbon monoxide in the atmosphere in very, very, very small trace amounts. Another reservoir for carbon, we could say, is in the Earth's crust. And so the Earth's crust, carbon is contained in the soils that are on the surface of the Earth, also in carbonate-containing rocks and minerals, and then also deep below the surface of the Earth, underground, you'll find carbon in fossil fuels. Fossil fuels consist of crude oil, where you can find a mixture of hydrocarbon compounds, and then coal. Coal is made of many different types of atoms that are bonded together: sulfur, nitrogen, hydrogen, oxygen, but also carbon. And carbon's elemental percent composition in coal is the highest of all of the atoms that compose coal. Carbon is in the highest percentage. And then also you have carbon in natural gas. Natural gas consists mostly of methane, CH4. Now, carbonate-containing rocks, carbonate is a polyatomic ion. Has the formula CO3 with a charge of a -2. And one of the more popular types of carbonate-containing rocks is calcium carbonate. Calcium carbonate is also known by the common name limestone. So calcium carbonate consists of the polyatomic ion carbonate, CO3, and the polyatomic ion CO3 2-, and a calcium metal ion, Ca2+. So calcium carbonate consists of a metal and a nonmetal polyatomic ion. So therefore, calcium carbonate is one of many types of ionic compounds. So here our picture. This is a picture of the carbon cycle. We talked about the 4 different reservoirs where carbon exists. Here's the atmosphere. The Earth's crust, you have the carbonate containing minerals and rocks. You also have the soils and fossil fuels. So the Earth's crust is the second of the 4 different types of reservoirs. The third type of reservoir, different carbon containing compounds and molecules exist in plants and animals. And in plants and animals, carbon is usually combined and bonded together with hydrogen, oxygen, and nitrogen atoms. And the different types of molecules that are found in plants and animals are specifically called macromolecules. These are things like proteins, fats, and carbohydrates. So there's a tree there representing another reservoir, the forest. And then the 4th type of reservoir are surface and ocean waters. Carbon dioxide gets dissolved in the surface and ocean waters. And so the second reservoir we talked about, those carbonate containing rocks like calcium carbonate, we said that calcium carbonate is an ionic compound. Ionic compounds are called ionic compounds because they are made up of ions. Ions are basically atoms, or in the case of a polyatomic ion like carbonate, it's a group of atoms that have gained or lost one or more electrons. And in the process of gaining or losing one or more electrons, the atom goes from being neutral with no charge to becoming ions that are charged. And so the types of atoms that tend to lose electrons are metals. So to have a neutral atom means that you have an equal number of protons and electrons. So if an atom having an equal number of protons and electrons, then loses one or more electrons, then it's going to result in forming an ion that is positively charged. Positively charged ions are called cations. And the reason why it is positively charged is because if it started out as a neutral atom with an equal number of protons and electrons, and then that metal atom loses one or more electrons, then it's been converted to a positively charged cation because it now has more protons than electrons. And then if you have an atom that gains one or more electrons, and nonmetals tend to do this, the atom which was neutral, if it gains one or more electrons, the result is that it now has more electrons than protons, and therefore has an overall negative charge. Negatively charged ions are called anions. So ionic compounds are composed of ions, and these ions are present in fixed proportions. Like calcium carbonate, it consists of one calcium ion and one carbonate polyatomic ion. And then they come together to form the calcium carbonate ionic compound. And ionic compounds, just like all compounds, are overall neutral because the positive 2 charge that the metal calcium cation has gets canceled out by the negative 2 charge that the polyatomic anion has. And so when they combine, they do so because their opposite charges attract each other and they form an ionic bond. And those charges neutralize each other out. And so ionic compounds are present in fixed proportions, like calcium carbonate. It consists of one calcium ion and one carbonate ion, and it will always exist that way in nature. In addition to having ions present in fixed ratios or proportions, ionic compounds are also arranged in regular geometric shapes and structures. Ionic compounds generally always will contain a metal cation that's positively charged and a nonmetal anion that is negatively charged. That is in general. There are some exceptions. So here we have our periodic table. And I like this periodic table because it is color-coded. And so we can see here that shown in red are the alkali metals. And these alkali metals represent group 1A. And as we learned in chapter 3, elements in group 1A have one valence electron. And we also learned in in chapter 3, that only the valence electrons participate in bonding. So when we learn how to draw Lewis structures, we had to take the formula of a molecular compound and add up the number of valence electrons represented by each atom that makes up the formula of the compound. And that gave us our total required number of valence electrons to show in the Lewis structure. So only the valence electrons participate in bonding and bringing atoms together in a bond to connect them in order to form a compound. So therefore, the alkali metals of group 1A in forming ionic compounds, they have only one valence electron, so they will lose only one electron. And so when they lose one electron, they will have a -1 charge. So when the group 1A alkali metals change from being atoms to ions by losing one electron, they will have, a +1 charge. Next to group 1A, you have the alkaline earth metals shown here in orange, like a Tennessee orange color. Group 2A. They have 2 valence electrons, so they can lose 2 electrons. And when they do, they're converted from an atom to an ion with a +2 charge. So now if we jump over to group 3A, we notice we have boron. Just like in group 1A, we had hydrogen shown in green. And those green colors represent nonmetals. So hydrogen is a nonmetal. And then boron is a metalloid, shown there in yellow. So are silicon and germanium in group 4A. And arsenic and antimony in group 5A. And tellurium in group 6A. Those are all metalloids. But looking further down into group 3A, you see aluminum, gallium, so on and so forth, shown in purple. The purple are the post-transition metals. So these guys here are metals. So for group 3A, the ones that are metals, they therefore can lose 3 electrons because they have 3 valence electrons. And they become +3 charged ions. So moving on to group 4A, you've got carbon, which is a nonmetal. Then you've got your silicon and germanium that are metalloids. Underneath them, you have 2 metals, tin, Sn, and lead, Pb. So the group 4A metals, which are only tin and lead, they have 4 valence electrons. They can lose those 4, or they can lose 2. And therefore they can form +2 or +4 charge ions. So tin and lead are special because they can form 2 types of metal cations, either with a +2 charge or a +4. And so now that we've looked at group 4A, the metals in that group, there's also one nonmetal in this group, carbon. So carbon, being a nonmetal, it can gain 4 electrons. And then it can have an ion with a -4 charge. So remember, nonmetals gain electrons, and therefore when they become ions, they have a negative charge. The next you got group 5A. The 2 nonmetals are nitrogen and phosphorus. So 5A, nonmetals. The nonmetals of course, they gain electrons. So the 5A, they have 5 valence electrons. And so therefore, they want to gain enough electrons so that they have 8 valence electrons. So that's why carbon has 4 valence electrons, and therefore can gain 4 valence electrons in order to have a total of 8. So the group 5A nonmetals, having 5 valence electrons, they can gain 3 electrons, and they become a -3 charge ion. Then next we've got group 6A. There are nonmetals there, and then group 7A nonmetals are shown here. The group 6A nonmetals, they have 6 valence electrons, so they can gain 2 electrons, and then have a -2 charge as ions. And then finally, the 7A nonmetals. They have 7 valence electrons. So therefore, they're only one group away from the 8A noble gases. The 8A noble gases are stable. They have 8 valence electrons, so they neither need to gain nor will they lose electrons. They're perfectly stable just the way they are. So therefore, noble gases in group 8A, they do not make bonds with any other types of atoms, nor do they make bonds with themselves or other group 8A nonmetal noble gases. They stay as single ions in nature. They do not bond. They like to be alone because they're stable and happy. Alone because they have 8 valence electrons. So the group 7A nonmetals have 7 valence electrons. Excuse me. And they are 1 electron short of having 8. So they want to gain 1 electron. And they become -1 charged ions. So that takes us through the periodic table and the types of ions that form. For the metals, they lose electrons, become positively charged ions, and the nonmetals gain electrons to become negatively charged ions. Now notice that we skipped these guys, shown here in the light blue, the transition metals. So the reason why we skip these is because they can have various charges. They're metals, so they're going to lose electrons. Well, how many will they lose? Well, it depends on the transition metal. They can lose 1, they can lose 2. Some transition metals, just like tin and lead, can form more than 1 metal cation. For instance, iron, Fe. Iron can lose 2 electrons and become a +2 charged metal cation, or iron can lose 3 electrons and become a +3 charged metal cation. So we'll talk a little bit more about the transition metals and the types of ions they form here in a few minutes. So taking a look at the group 1A alkali metal, sodium, with 1 valence electron, sodium will lose that 1 valence electron and become the sodium cation with a +1 charge. So you notice here, you just see the plus without a number next to it. So if there's not a number next to that superscript plus sign, it's understood to be 1. And then chlorine, a group 7A nonmetal, it will gain 1 electron and become the chlorine -1 anion. And so these 2 ions, Na+1 and chlorine -1, they combine together to form an ionic bond and therefore an ionic compound. The +1 and -1 charges cancel each other out, and you form a neutral ionic compound. And this is called sodium chloride. So in completing this table, the sodium atom has the symbol Na. It is atomic number 11 on the periodic table. So there are 11 protons and 11 electrons, and it does not have a net charge because it's a neutral atom. But the sodium ion has a charge. And because sodium belongs to group 1A, it can only lose its one valence electron, and therefore will become a positive one charged ion. So its symbol is Na plus, or Na plus 1. It has still 11 protons, but after losing one electron now, the ion only has 10 electrons, and the overall net charge is plus 1. Now, neon is one of those group 8 noble gases. It's atomic number 10, so it has 10 protons, and it's an atom, it's neutral. So it has 10 protons, 10 electrons, and no net charge. The chlorine atom, chlorine is atomic number 17. So it has 17 protons, 17 neutrons, and no net charge. The chloride ion, being a group 7A nonmetal, 7 valence electrons, so therefore it wants to gain 1 electron and become negative 1 charged. So it's still chlorine, so it still has 17 protons. After gaining 1 electron, the chloride ion has 18 electrons and an overall net charge of negative 1. Argon is also a noble gas. It is atomic number 18, so it has 18 protons. It's a neutral atom. Eighteen protons, and therefore, being neutral, it also has 18 electrons and an overall net charge of 0. So what you'll notice here is that the argon atom and the chloride ion have the same number of electrons. So does the sodium ion and the neon atom. So anytime two species have the same number of electrons, it's said that those two species are isoelectronic. The same is true for the chloride ion and argon. So we already took a look at the joining together of the sodium and the chlorine ions. Their charges cancel each other out, and you form your neutral ionic compound. Same thing happens with lithium, a group 1 metal cation, and fluoride, a group 7A nonmetal anion. The plus 1 charge gets canceled out by the negative 1 charge, and you form LiF, which is lithium fluoride. And then finally, we've got the magnesium cation from group 2A. So it has 2 valence electrons that it can lose and form an Mg2+ cation. If you combine it with a sulfur 2- anion, the +2 charge gets canceled out by the -2 charge. You have MgS, which is magnesium sulfide. So this next version of the periodic table is very helpful because it shows you the more common monoatomic ions. And they're called monoatomic, mono meaning one. They consist of only one type of atom. That's the opposite of a polyatomic ion that consists of many atoms. So you see your group 1A cations having a +1 charge. And again, the 1 is missing. It's understood to mean 1. And the group 2A with the 2+ charges. Then jumping over to group 3A, we can go ahead and add gallium and indium and thallium to that list. And again, in 4A, the only metals are tin and lead, each having 2 possible types of cations that form. And then we go into the nonmetals. I'll go ahead and add carbon to this with a 4-, phosphorus and nitrogen both with -3 charges because they're in group 5A, and therefore they want to obtain 8 valence electrons to be stable, so they need to gain 3. The group 6A nonmetals, they need to gain 2 electrons, so therefore they have a -2 charge as ions. Whereas the group 5A nonmetals gaining 3 electrons, they have a -3 charge. And then finally, the group 7A nonmetals, they will only gain 1 electron to have a -1 charge. So this is a very helpful little periodic table to have next to you to look at the various ions that can form and their associated charges. Now, looking here in on the group, the different groups that we looked at, now let's move back to the middle of the periodic table and look at the transition metals. And so, like I stated, the transition metals, they can form various charged metal cations. For example, chromium can either form a Cr3+ metal cation, meaning it's lost 3 electrons, or it can lose 6 electrons and form the Cr6+ cation. Iron can either lose 2 electrons or 3 electrons. The same is true for cobalt and nickel. Copper, on the other hand, it can either lose 1 electron or 2. And then the other 3 will only form 2+ charged cations. Now, to look at a few more, you got gold right underneath. Silver is Ag. Gold is Au. Gold can form either a +1 cation or a +3. And any other notable ones? Platinum is right next to gold. There's platinum PT. And I think platinum mostly forms a +2 cation, if I'm not mistaken. So I think this gives us a good foundation for the more popular monoatomic cations that can form. So now we looked at the formation of these three ionic compounds, and we noticed that the charges perfectly balanced each other out. You had a +1 charge being canceled out by a -1, or a +2 charge being canceled out by a -2 charge. So here we've got three more ion pairings to look at, but we notice that the charges do not initially cancel each other out. If we bring the magnesium 2+ cation together with the chloride -1 anion, a +2 charge cannot get canceled out by a -1 charge. So whenever the charges don't cancel each other out straight away, that means you need more than one or both of the ions in order for them to their charges to cancel each other out. And so we need a total of a -2 charge in order to cancel out the +2 charge. So in order to do that, that means we need 2 chlorine ions. And then we'll balance it on the left side. Remember how we balance equations. We learned that in chapter 2. So now that we've got 2 chlorine ions, each of those 2 chlorine ions having a -1 charge, that gives us an overall -2 charge. So now those charges cancel out. So our ionic compounds formula is MgCl2. Next, we've got an iron cation with a 3+ charge and an oxygen anion with a -2 charge. Well, here we have another situation. A +3 charge can't get canceled out by a -2 charge. So just like when we were balancing equations, whenever we have a 3-2 situation, we think least common multiple between 3 and 2, which is 6. So that means we've got to convert our 3+ charge into a 6+ charge. And to do that, we need 2 iron cations. And then the -2 charge needs to become a -6 charge. So to do that, we need 3 oxygen ions. Each of those 3 oxygen ions has a -2 charge, collectively giving you a -6 charge. So now those charges cancel out, and your ionic compound formula is Fe2O3. The last one, we've got copper with a +1 charge and an oxygen with a -2 charge. Well, the +1 can't cancel out a -2. We need to have an overall +2 charge. So to do that, we need 2 copper ions. Overall, now we have a +2, which cancels out the -2. So our formula is Cu2O. So now we've been writing formulas for ionic compounds in which all of our ions are monoatomic. But an ionic compound can consist of a polyatomic ion. A polyatomic ion consists of 2 or more types of atoms that are covalently bonded together. to have an overall positive or an overall negative charge. Our monoatomic ions only consist of one type of atom, but the polyatomic ions have two or more atoms. Polyatomic ions are fairly stable, and they often stay together in a reaction. Most of the polyatomic ions that exist are negatively charged and therefore are called polyatomic anions. But there are a few positively charged polyatomic ions. The more common popular one is ammonium. It has a +1 charge, NH4+. The only other popular polyatomic cation, and I don't think it's on this list, no it's not, is the hydronium ion. And it has a formula H3O+. But the rest of the polyatomic ions in this table are negatively charged. So this is a good table along with the polyatomic, the monoatomic ions periodic table. You want to have this handy when you're working on homework and quizzes for this chapter. And you'd also want to have a polyatomic ion table like this one handy as well. You don't have to memorize these polyatomic ions. You just need to have this table or one like it handy to refer back to. Then also shown, just like in this monoatomic ion table, those transition metal cations. And some of the more popular ones are also listed here, like our 10-2 and our 10-4, one with a 2+ charge, one with a 4+ charge, so on and so forth. Your iron, you can have a 2+ or a 3+, copper a +1 or a 2+, so on and so forth. So this is a good reference table. So when I formed the formulas for these ionic compounds involving monoatomic ions, I gave you the names. So let's write the names for these as well. Magnesium chloride. This one is iron 3 oxide. And this one is copper 1 oxide. And like our little handy table here tells us, iron can also exist as a 2+. As a 2+ cation. And therefore those charges cancel straight away. So you can also have FeO, which is iron 2 oxide. Then you can also have, in addition to copper 1 oxide, you can also have copper 2 oxide. And so the name copper 2 oxide, the Roman numeral 2 represents the charge that that metal possesses. So for copper 1 oxide, the charge on the copper is +1. For copper 2 oxide, the charge on the copper is +2. Same thing for iron 3 versus iron 2 oxide. Iron 3 oxide, the charge on the copper is +3. Iron 2 oxide, the charge on the iron is +2. So to name ionic compounds, there are several rules that govern the naming of ionic compounds. When we learn how to name molecular compounds, we noticed that the rules were pretty cut and dry. You name the first nonmetal, you name the second nonmetal, you drop the ending of the name of the second nonmetal, replaced with IDE, and then you use prefixes to denote the number of each of the types of atoms that exist in the formula, using those Greek prefixes, mono and di and tri, tetra, penta, hexa, so on and so forth. The rules for naming ionic compounds are a little bit more detailed and a little bit more involved than for naming molecular compounds that consist only of nonmetals. Ionic compounds consist of a metal and a nonmetal. So depending on whether or not your metal is a group 1 or group 2A metal versus the metal being a transition metal, your rules for naming are going to be a little bit different. So let's take a look at the first rule. If your ionic compound is composed of a group 1A or a group 2A metal and a monoatomic nonmetal anion, which is also called a binary ionic compound, you name the metal ion name plus the nonmetal ion name, and then drop the ending of the nonmetal ion name and replace it with IDE. And so shown here are some examples. The second rule is when your ionic compound is composed of a group 1A or 2A metal cation and a polyatomic anion. The rule says you name the metal ion name and then you name the polyatomic ion name. That's it. You don't drop the ending of the name of a polyatomic anion. So here are some examples shown here. KClO4. We look at our polyatomic ion table. ClO4 is perchlorate. So therefore, this is potassium perchlorate. Rule number 3. If your ionic compound is composed of a transition metal cation and a monoatomic nonmetal anion, you name the metal ion's name, and then next to it you put parentheses, and inside the parentheses will be your Roman numeral. Your Roman numeral indicates the charge on the metal. And then after that, you add the nonmetal ion name. And you need to drop the ending of the nonmetal ion name and replace it with IDE. So we just looked at iron 3 oxide, Fe2O3. FeCl3 is iron 3. FeCl3 is iron 3 chloride. CuBr2 is copper 2 bromide. So how did we know that this was iron 3 chloride and not iron 2 chloride? Well, chlorine is in group 7A, has a -1 charge. And so we need 3 of them in order to balance out the -3 charge. So the charge on the iron is +3. And then FeCl2 is iron 2 chloride. So therefore, there are 2 chlorines to balance out the +2 charge on the iron. The fourth scenario is when you have an ionic compound that's composed of a transition metal and a polyatomic nonmetal anion. You name the metal ion, put your parentheses, in the parentheses, add your Roman numeral, and then you add the polyatomic ion name, and you do not drop the ending ever of a polyatomic ion's name. And so here are some examples. Copper 1 phosphate. Copper, there's 3 of them in the formula, and so the charge is +1. The phosphate polyatomic ion, going to our polyatomic ion table, is PO4 with a 3- charge. So therefore you need 3 coppers, each one with a +1 charge, to balance out the -3 charge of the polyatomic ion. So Cu3PO4, and the charge on the copper is +1. So that's why we have copper 1 phosphate for our name. And remember, in our polyatomic ion table, we listed the popular common polyatomic ion ammonium that has a +1 charge. So whenever ammonium is a part of your ionic compound name, we're looking at rule number 5. So you add the name of the ammonium polyatomic cation, ammonium, and then if you are paired with a monoatomic anion, you add the monoatomic ion's name, and then you drop the ending and replace with IDE. But if ammonium is paired with another polyatomic anion, you just name the name ammonium, and then you add the polyatomic ion name, and that's it. You never drop the ending of the name of a polyatomic ion. So now to look at these questions. We've got the sodium monoatomic cation with a +1 charge, and then we've got a sulfate polyatomic ion. I like to put my polyatomic ion in parentheses, and the charge for that polyatomic ion, I like to put on the outside of the parentheses while I'm working to figure out the formula, the correct formula. So I see that a +1 charge can't cancel out a -2. I need a +2 charge in order to cancel out the -2. So that means I'm going to need 2 sodium ions. So now the charges cancel, and I get Na2SO4. Next, we've got an aluminum cation with a +3 charge and an acetate polyatomic ion with a -1 charge. A -1 can't cancel out a +3. I need a -3 to cancel out a +3. So that means I need 3 acetate polyatomic ions. Now the charges cancel. If I have more than 1 polyatomic ion involved, then you have to put the polyatomic ion in parentheses and put the subscript outside the parentheses to indicate the number of those polyatomic ions. Next, we have the carbonate polyatomic ion, CO3 2-, and we're going to pair it with a potassium ion, K+. You normally put the metal first in the ionic compound. That's just normally how you see it in textbooks, but it really doesn't matter as long as everything is correct. And then we've got CO3. I'll put that in parentheses. That's my polyatomic ion. And the charge is 2-. I put that outside of the parentheses. So it's clear that a +1 charge cannot cancel out a -2. I need a +2. in order to cancel out that -2. So I need 2 potassium ions. So now the charges cancel, and my formula is K2CO3. And because I only have one CO3 polyatomic ion, and I don't need to put the 1, I don't have to use parentheses. Only if I have more than one of the polyatomic ions do I, in the end, put the polyatomic ion in parentheses and put the subscript that accompanies it outside of the parentheses. So now we need our naming rules to name each of these. And so I have potassium, K, that's a monoatomic ion. So the rules say I name it. And then I've got a polyatomic ion, NO3. I go to my polyatomic ion table. NO3 is nitrate. It has a -1 charge. And so I'm looking at the rule for a monoatomic metal ion and a polyatomic ion. That's rule number 2. So I name my metal ion name, and then I name the polyatomic ion name. That's all I need to do. So this would be potassium nitrate. The next one, FeSO4. I've got a transition metal, iron, and I've got a polyatomic ion sulfate. So always take a look at your formula and analyze if you have a group 1 or group 2A metal, or do you have a transition metal? And then look at your anion. Is it a monoatomic anion or is it a polyatomic anion? So my rule for a transition metal and a polyatomic anion, the rule says I name the metal ion name and then parentheses and a Roman numeral, and then add the polyatomic ion name. So I have iron, and I put my parentheses, and then SO4, go to my polyatomic ion table. See why it's important to have this table handy. SO4 is sulfate. So iron, sulfate. Now I've got to figure out, well, what Roman numeral goes in the parentheses? Is it 2 plus or is it 3 plus? So do I need a Roman numeral 2 for a 2 plus charge on that iron metal? Or do I need a Roman numeral 3, meaning that there is a 3 plus charge on the metal? So what does the metal iron carry as its charge? Is it +2 or is it +3? So let's figure that out. Sulfate is our polyatomic ion. It has a -2 charge. So iron is going to have to cancel out that -2 charge. And we notice from the formula that we only have one sulfate. So we've got SO4, 2-, and then we have our Fe. So to cancel out that 2-, iron has to be 2 plus. So we need a Roman numeral 2 in our parentheses. Next, we've got CrPO4. So we've got the same rule, rule number 4, transition metal, and PO4, a polyatomic ion. PO4, what's the name of that polyatomic ion? Phosphate, PO4 with a -3 charge. So therefore, our rule says we name the metal chromium, parentheses, with the Roman numeral in it, and then name the polyatomic ion. So chromium, going back to our little table, it can either have a +3 charge or a +6. So what Roman numeral do we need? Do we need the Roman numeral 3 or do we need the Roman numeral 6? Let's figure it out. Well, we looked at our polyatomic ion table for phosphate, and it has a -3 charge. And in our formula, we only have one phosphate with a -3 charge. So the chromium has to balance out that -3. So chromium's charge must be +3. So we need a Roman numeral 3 in our parentheses. And then last, we've got copper nitrate. Nitrate is a polyatomic ion. Copper is a transition metal, so we're still working with rule number 4. And nitrate is NO3, has a -1 charge. So we have copper, parentheses with a Roman numeral, and then nitrate. So what Roman numeral do we need for copper? Cu is copper. It's either going to be a +1 or a +2 charge. So either a Roman numeral 1 or a Roman numeral 2. Which do we need? So we have in our formula, we've got 2 nitrates. Each nitrate has a -1 charge. So that's an overall -2 charge. So the copper has to balance out this overall -2 charge. So we need copper's charge to be +2. So we need a Roman numeral 2 in our parentheses. Last question. We've got the names given to us for these ionic compounds. And so we need to take the name and figure out the formula. So the first one is sodium hypochlorite. So this is a polyatomic ion. And this is a group 1A metal. And so when you have the group 1A or group 2A metals, no Roman numeral is needed. So you notice in the name for sodium hypochlorite, there are no parentheses and Roman numerals because group 1A metals and group 2A metals don't require that. They have a set charge. Group 1A metals have a +1 charge. Group 2A metals have a +2 charge. So figuring out the formula, we've got sodium with its +1 charge. Hypochlorite is a polyatomic ion. Let's go to our table and find hypochlorite. And there we are. It has the formula ClO -1. And then the +1 charge cancels out the -1 charge. So your formula is NaClO. The next one, nickel 2 chloride. That is telling us that the nickel has a +2 charge. Chloride, that's a monoatomic ion. Chlorine. Chlorine has a -1 charge. Well, a -1 charge cannot cancel out a +2 charge. So we're going to need 2 of them. So now the charges cancel out. So you have NiCl2. And then finally, iron 3 oxide. Iron 3 means we have a 3+ charge. Oxide, that's oxygen with this ending dropped and replaced by IDE. Oxygen has a 2- charge. So a +3 can't get canceled out by a -2. So we think least common multiple between 3 and 2 is 6. So we're going to need an overall 6+ charge. So we're going to need 2 iron ions. And we're going to need an overall -6 charge. So we're going to need 3 oxygen anions. So now those charges cancel out. And your formula is Fe2O3. And that brings us to the end of this recording for part 1 of the chapter 4 notes.